This lesson we're going to start learning about the trigonometric functions, primarily the sine and the cosine function. To begin talking about the sine and the cosine function, we need to look at the unit circle. This picture that you're seeing here is a picture of the unit circle. The unit circle is a circle that's centered at the origin, so this point right here is at 0, 0 on the origin for the xy axis. And this being the x-axis, this being the y-axis. So it's centered at 0, 0 on the xy axis, and it has a radius of 1. The equation of that circle is this equation right here, x squared plus y squared equals 1. Now you may not be familiar with equations of circles, but an equation of a circle has this form: x squared plus y squared equals r squared, where the center of this circle would always be at 0, 0, but the radius of the circle changes depending on what r is. Okay, so r squared, this number right here is r squared. In this case, that's 1 squared is 1, so the radius is 1. We're primarily going to stick to this unit circle to start, but then eventually we're going to start looking at any circle with any radius. Alright, so with this unit circle, right, you should be familiar now with the angles inside the circle. This was the purpose of the last lesson, was to get you familiar with the fact that there are common angles: 30 degrees, 45 degrees, 60 degrees, 90 degrees. Okay? And in radians it would be pi sixths, pi fourths, pi thirds, pi halves. And when we look at these common angles, then we can take multiples of those common angles and start working our way around the circle. So we have 120, or 2 pi thirds, 135, 3 pi fourths, and so on. And at this point, you should be familiar with what angles fall where. If I said 30 degrees, you know it falls in quadrant 1. If I said 210 degrees, you know it falls in quadrant 3. If I say 11 pi 6, you know it falls in quadrant 4. So this is what you're going to have in your knowledge to be able to move forward. Now what we're going to have to start looking at is the idea of these points that are associated with the unit circle. Okay? Because these points that are associated with the unit circle, this point here, square root of 3 over 2, comma 1 over 2, and so on, are the points we're going to use to help us evaluate what we're going to call the sine and the cosine function. And this is fairly intimidating when you look at it at first, but there's a pattern to how this whole thing develops, and as long as you have the angles inside down at this point, then you should be able to do the points around the outside. Now if you still are having trouble with the angles inside the circle, there's a little trick that you can use to help you remember some of this. Like if I said, where's 11 pi sixths, right? So 11 pi sixths is here. What I would do is I would relate 11 pi sixths to a whole number multiple of sixths. So in that case, what I'm saying is you would look at, say, 12 pi sixths. Okay? 12 pi sixths would simplify to a whole number, right? Because 12 over 6 is 2, and this is actually 2 pi. So if I know where 2 pi is, and everyone should know at least where 2 pi is, then 11 pi sixths, comparable to 12 pi sixths, or 2 pi, is smaller. So if 11 pi 6 is a little smaller than 2 pi, or 12 pi 6, that puts me, here's 2 pi is right here, a full rotation, so I should just back it up a pi 6, and that's where 11 pi 6 will fall. If I go, say, 7 pi 6, and I want to figure out, okay, where's 7 pi 6? I can't remember where that falls. Well, I try to think of what's a whole number that I can work with that's really close to 7 pi 6. That would be 6 pi 6. So 6 pi 6 is the same thing as pi, and I know where pi is. 6 pi 6 and pi are the same, and I know that pi is right here. So if I want to try and find where 7 pi 6 is, well, 7 pi 6 is bigger than 6 pi 6. Well, how much bigger? A pi 6 bigger. So if I know where pi is, and I have to just go a pi 6 further around the circle from that, like I'm traveling this way, I go to pi, I got to go another pi 6 further than that, that puts me right here. So that's sort of the easy way to remember these things. Or let's say 5 pi 6, right? I'll take 5 pi 6 and relate it to 6 pi 6 as well, but that's a little bit smaller. So I have this like 6 pi 6, which is pi. I have 7 pi 6, and I have 5 pi 6. So I go, okay, well 7 pi 6 is bigger, 5 pi 6 is smaller. So if I know 6 pi 6 is right here, then I'll go back a little bit to get 5 pi 6 and forward a little bit to get 7 pi 6. And that can tell me kind of where these angles fall, and I think that's the quick way to kind of remember where these are if you still are having trouble remembering where each one of these special angles falls. Alright, so now that we have this picture, we're going to have to start learning about these points on the outside. Alright, so here's what we need to learn about when it comes to these functions. There are two functions that we're going to learn about in this lesson, and they're the sine and the cosine function. Altogether there are 6 trigonometric functions, but we start off only learning about 2, because these 2 trigonometric functions are the basis for all the other ones. So we're going to learn about the sine function, okay, the sine function, the sine of theta. We abbreviate the sine of theta using sin parentheses theta, and here we're taking the sine of an angle. Okay, we also have the cosine of theta that we're going to learn about, and we abbreviate that cos parentheses theta, and that's the cosine of theta, the cosine of this angle. So these trigonometric functions are functions of an angle, okay, functions of theta, beta, alpha, whatever angle you're dealing with. So you have the cosine of theta and the sine of theta. Now we define these in this way. If theta is an angle in standard position and xy is a point in the intersection of the terminal side of the unit circle, then the sine of theta equals the y coordinate of that intersection, and the cosine of theta equals the x coordinate of that intersection. So here's the idea, right? We're looking at, say, a unit circle. I just sort of blew up the first quadrant here. So I have this first quadrant. This is my y-axis. This is my x-axis. Here's the unit circle. I'm going to take some angle in that unit circle. So here's my angle, theta. That angle's terminal side, which is right here, because it's in standard position, right? The key is that part of the definition says standard position. If my angle's in standard position, the terminal side of that angle will intersect the circle somewhere, and then it will intersect the circle at a point. It depends on how far I rotate as to which point I intersect, but it will intersect the circle at a point. Okay? That point should have an x coordinate and a y coordinate. So we're going to define the sine of theta, okay? The sine of this angle will be defined by looking at the y coordinate of this intersection point. And the cosine of theta will be defined as the x coordinate of this intersection point. So we're relating basically what these two functions do. If you think of them as a function, right, that goes from here to here, what they do is they match an angle theta with either a y coordinate, that would be for the sine of theta function, or they match an angle with an x coordinate, and that would be for the cosine of theta function. Okay? And that's how these functions work. Like, you have certain functions that we've already learned about, like the squaring function. What do? They match a number with the square of that number. Well, these functions match an angle with an x or y coordinate based off of an intersection point with this angle's terminal side and the unit circle. So if you know the intersection point for certain angles, then you know what your answers are going to be for given angles. And that's sort of what we need to learn, is we need to get used to these intersection points. So if I start to look at this here and I say, all right, well, here is the first quadrant of the unit circle, and we're going to have to get used to learning these points. Okay. Well, if I start to look at these points, I say, okay, well, what's the sine of 30 degrees? And it doesn't matter whether you do degrees or radians, because it's the same angle, just depends on how you want to measure it. If I want to do the sine of 30 degrees, if I know where 30 degrees is in the unit circle, it's right here. Here's my angle, theta, it's 30 degrees. If I know the intersection point for the terminal side on the unit circle, this is it right here, then I can find the sine of 30 degrees by primarily just looking at the y coordinate. The y coordinate's a half, so the sine of 30 degrees is a half. If I want to find the cosine of 30 degrees, okay, I have to look at the x-coordinate for that intersection point. That's square root of 3 over 2. So the cosine of 30 degrees is square root of 3 over 2. If I did it with radians, it's the same thing. The cosine of pi 6, which is also the same thing as 30 degrees, is square root of 3 over 2. Because that's the same intersection point. I just measured the angle with radians instead of degrees. So if I know these intersection points here, here, and here, I can find the sine and cosine of these angles. And that goes for all the special angles around here. Now, if it's some angle like, I don't know, an angle that falls here, say 72 degrees, right? 72 degrees would fall right there. In order to find the sine or the cosine of 72 degrees, I need to know this intersection point. Well, that's not as easy because I can't remember all the intersection points for every single angle in a unit circle. It's impossible. What we do is we get used to the ones that come up most often, our special angles, and we get used to these. And then eventually, if we know these, we can then use that to help us find other angles. Well, maybe not 72 degrees, but at least some other angles that maybe we can combine these multiple angles to get another angle. So we'll get to that. That's farther, way farther down the road. But right now we need to get used to these. So one thing you're going to see, if you're going to be looking at the x-coordinates and the y-coordinates for your cosine and sine function, then we're looking at domain. Well, domain for each function, any function, and all the values that you can plug in this case theta. Theta would be my domain values. Well, as long as I can take an angle, so I have, say, sine of theta, as long as I can take some angle and plug it in and get an answer, then it will be in my domain. Well, no matter what angle I look at around the unit circle, that angle is always going to intersect the unit circle, okay? And it's always going to have a y-coordinate. So every angle I use when I take the sine of it, I will always have an answer for. Now, what the answer is isn't that easy to find, but you'll always have an answer for it. Well, if that's the case, that means I can let theta be anything, any angle around the circle, in any rotation, positive, negative, doesn't matter, will always give me an answer. If that's the case, then the domain for the sine function should be all real numbers, negative infinity to positive infinity. Same thing for cosine, because you'll always get an x-coordinate as well. So the domain for cosine is all real numbers, or negative infinity to positive infinity, which means you can take anything and plug it into the sine or the cosine. Now the range, however, which are the answers that come out, in this case for the sine are the y-coordinates, and for the cosine it's the x-coordinates, will be negative 1 to 1. Because if I go back to my unit circle, full unit circle picture, if I'm looking at all the x's and y coordinates in this unit circle, the biggest y coordinate I'll ever get is 1, and the smallest y coordinate I'll ever get is negative 1, and whether the angle's in this side or this side, I'll have y values between negative 1 and 1. Okay? So all my answers will always be between negative 1 and 1 when it comes to the y-coordinates, which comes to sine. So that means the range, or the answers I'm getting out of the sine function, are between negative 1 and 1. Same thing goes for cosine. The biggest x value is 1. The smallest x value is negative 1. And all the angles here or here will give me x values between negative 1 and 1. So if they give me x values between negative 1 and 1, cosine is, whenever I take the cosine of any angle, I will always get an answer between negative 1 and 1. So the range for cosine is also negative 1 to 1. So it's important to understand the domain for these functions and the range for these functions. You can plug any angle you want into sine and cosine. The only answers you will ever get from sine and cosine are answers between negative 1 and 1. You will never take the cosine of some angle and get an answer of, say, 2. That's impossible. It'll never happen because the answers for cosine will always have to be x-coordinates. In this case, the x-coordinates are only ones that are possible here are x-coordinates between negative 1 and 1. So that's just an important thing to understand with these functions. So now we need to start looking at these points a little bit closer. So the easiest points to remember are what we call the quadrantal angle points. Those are angles that fall on the axes. Because I think those are the angles, one, that you remember the most, but two, the points are really simple. Remember, this is a unit circle. So if it's a unit circle, the radius, if I go this distance here, is 1. Well, if that distance is 1 and this is the origin, then this point right here if I'm looking at this point on the x-axis, should have an x value of 1 and a y value of 0. And the same thing in all directions. If the radius this way is 1, then this point should have an x value of 0, but the y value should be 1. This point right here should be negative 1, 0, and this point right here should be 0, negative 1. So if I'm looking at what these angles are, well, the angle that starts in standard position right here and doesn't go anywhere, that would be 0 degrees or 0 radians. The angle that goes a quarter of the way around the circle and ends up right here would be 90 degrees or pi halves. The angle that goes halfway around the circle, that sits right here, okay, would be pi or 180 degrees. And the angle that goes 3/4 of the way around the circle would be 270 degrees or 3 pi halves. And if I go all the way around the circle, that's 2 pi, which is coterminal to 0 or 360 degrees. So these angles are some of the easiest ones to remember, but also the points that go along with them are the easiest ones as well. There's not much you have to do other than realize that since we're in a unit circle, the distance I'm traveling on each axis is 1 unit. So now if I want to say what's the sine of 90 degrees, it should be really easy to remember that the y coordinate there is 1, and sine uses the y coordinate. If I want to know what the cosine of pi is, well, again, because that's one of our quadrantal angles, it's an angle that falls on an axis, it should be fairly easy to remember that the x coordinate is negative 1. Sine of 3 pi halves, again, the y coordinate there would be negative 1. Cosine of 3 pi halves, the x coordinate there is 0. And the key is all these ones, if it falls on an axis, the answer is either 0, 1, or negative 1. Okay? No matter how many times I do this, like if I go around one full rotation, that's 2 pi, right? If I go down another half of a rotation, that's another pi. Well, I went 2 pi and then another pi, so that would actually be 3 pi. So 3 pi is coterminal to pi. Well, it's all the same. It falls on an axis. So if I want to know what the cosine of 3 pi is, again, because that is 2 pi plus another pi is 3 pi, I should get an answer of negative 1, okay, because that's the x coordinate. So maybe you have to draw a quick little picture to remember these numbers or something, but they should be fairly easy to remember, at least for this angle. Multiples of 90 degrees are our quadrantal angles. They fall on a particular axis. And the answers for all the x and y coordinates here should either be 1, negative 1, or 0. The harder angles to get used to are the ones that fall inside a particular quadrant. So let's start looking at multiples of 45 degrees. So 45 degrees would fall right here. This would be 45 degrees. Also, we could write this as pi fourths. Okay? So finding out what this point is going to be a little bit more difficult to come up with. Yeah, we know that this distance right here is 1, because it's the radius of the circle, but it's not easy to calculate 1 unit diagonally on the XY chart as easy as it is to calculate 1 unit vertically or horizontally. So we need to come up with this point. Now I'll tell you the point is this: square root of 2 over 2 for the x and square root of 2 over 2 for the y. Now where those numbers come from we'll see in 1 second. But here's the thing, if I look at another multiple of pi fourths, so let's look at this one. This angle right here would be 3 pi fourths. Okay? That angle is directly across from this one in terms of the y value. So the y value here should be square root of 2 over 2. Okay? It should be the same as that y value. So if I know this y value, I know that y value as well. And what happens is there's also symmetry involved because this is a circle. So whatever the x value is, okay, here, what happens is I should get that same corresponding x value just on the opposite side here. This distance here and this distance here should be the same because this is a circle and there's symmetry within my circle because I'm working off the center. Well, if the x value here for this point is square root of 2 over 2 and I'm just over on this side, well, it should just be negative square root of 2 over 2. So by knowing the point in the first quadrant, the multiple of pi fourths in the second quadrant really has the same form, just an x has to be negative because I'm in the second quadrant. Now if I look at the other multiple of pi fourths here, okay, well, same deal. If you look at it, if I follow it down, this one should be right above that one, which means this should have the exact same x coordinate as the one above it. And the y coordinate, again, because of symmetry, this distance here, and if I follow it, this distance here should be equal distances, this one just being negative, and since I'm in quadrant 3, the y value should be negative. I get negative square root of 2 over 2. This angle here, that's a multiple of pi fourths, would be 5 pi fourths. And then I go to the last one, the one right here. Okay. Again, if you kind of follow it, it should have the same x coordinate as the one above it. It should have the same y coordinate as the one across from it. So this one's going to be square root of 2 over 2 for the x and negative square root of 2 over 2 for the y. All four of these points have the same form because they're all related to the same angle, and these circles and these angles have symmetry to them. This angle would be, what, 7 pi fourths. Okay? So by knowing one of the angles points, the pi fourths, the first quadrant point, you really have the second, the third, and the fourth quadrant points that all relate to that same angle. And this is why it's helpful to realize which angles are multiples of other angles. We have our special angles, 30, 45, and 60, and everything around the circle is a multiple of one of those three. And it's important because the points are very, very similar, just knowing which coordinate has x or y being positive or negative. So now if I want to find the sine or cosine of any one of these angles, since I have the point, I can do that. Now where did that point come from? How do I know it's square root of 2 over 2 for the x and for the y? Well, you need to do a little bit of computation. Okay, so let's look at the first quadrant again. So you look at the first quadrant, here's our angle, 45 degrees. Oops, 45 degrees. Or pi fourths, whichever way you want to look at it. I like radians better than degrees, but whatever you want to do. It depends on the question that you're dealing with in the future. So we're trying to find this point. Well, there's a couple of things. One, this is the circle. That circle has the equation x squared plus y squared equals 1. This line is a line that cuts the xy axis directly in half. Well, the line that does that is the line y equals x. Okay? So what I'm trying to do is find the intersection between this line and this circle. The way you can always find the intersection between any two graphs is to take one and plug it into the other. So what I'm going to do is I'm going to look at this equation, x squared plus y squared equals 1. And I'm going to plug this equation into that. Well, this equation says that x equals y, or y equals x. So I can replace the x with a y or the y with an x. So I'm going to do this, x squared plus x squared equals 1. Since x and y are equal, I can take my y and put an x in its place. So what I get is 2x squared equals 1, x squared equals 1/2. Take the square root, I get x equals the square root of a half. Now whenever you take the square root of both sides of the equation, you got to do the plus and the minus. Okay. But the square root of a half, normally you would rationalize that, right? If I write this as x equals the square root of a half. In algebra, you learned that you should take the square root of 1 over the square root of 2. That's going to be 1 over the square root of 2. Then I should multiply by the square root of 2 over the square root of 2. And I get the square root of 2 over 2. Now remember, in the beginning there was a plus and minus in front of this whole thing, so if I travel that all the way through, I should have a plus and minus, which means that x should be positive or negative square root of 2, which we saw here in the first quadrant. This x value is the square root of 2 over 2. The positive one. If I travel along this same line, this line right here is the y equals x line. That line intersects the circle here, but if I travel all the way down here, it intersects the circle here as well. And what's the x-coordinate there? Negative square root of 2 over 2. So if you look, I have two answers for x, and that's because there's two places where this line intersects the circle, but generally that's where the square root of 2 over 2 comes from. Now what about the y value? Well, since this is on the line y equals x and y should be equal. So when are x and y equal? Well, when I'm on this line, what's the x-coordinate? Square root of 2 over 2, so the y-coordinate should be the same, square root of 2 over 2. If I'm on the other side of that line, if I'm down here, the x and y coordinates should be the same because I'm on the line y equals x. And again, if this one's negative square root of 2 over 2 for the x, then this one's going to be negative square root of 2 over 2 for the y. Now, that's not really all that important to know where the numbers came from. I want to show you where they came from just so you have an idea that they didn't just pop out of thin air. I mean, they come from some very, very basic computation, but largely what you're going to have to do is you're going to have to memorize these points. Because you're going to have to be able to say, what's the cosine of pi fourths? And you're going to have to right away repeat square root of 2 over 2. It should be like memorizing your times tables in second grade. Okay? When you first started learning your times tables in second grade, what happened? You had to do 2 times 3 or 4 times 5 or whatever it was, and it took you a while to think about what it was. And maybe you had a little table printout that you had taped to your desk, and you had to figure out what the answer was. But eventually you had to have that stuff memorized. So when the teacher said, what's 3 times 4? Boom, you spit the answer out. What's 5 times 5? Boom, you spit the answer out. Well, this is the same idea. What you want to do is get to the point where you're good enough with these special angles and these points that when I say, or when any other teacher says in the future, what's the cosine of pi fourths, you automatically just say square root of 2 over 2. What's the sine of pi fourths? Square root of 2 over 2. Okay? 3 pi fourths. Cosine of 3 pi fourths, negative square root of 2 over 2. And you can do that. Now it takes time. We're just learning this, and you're going to have to get used to memorizing these points and learning this unit circle, but eventually you should get to the point where you can do this. Now what you don't want to do, okay, what you absolutely don't want to do is if you go to your calculator and you say, okay, cosine of pi fourths, or probably if you're using your calculator, you're going to do the cosine of 45 degrees because it's easier to plug in degrees as opposed to radians in your calculator. Your calculator is going to give you some decimal number. And that decimal number is 0.7071067811186 blah 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 blah. It's just going to keep going and going forever. What happens is this is a decimal that goes on forever, never repeats itself. So if you're going to write this decimal answer, you're going to probably round it at some point. And maybe you might round it to like 1 or 2 decimal places. So you'd say, okay, the answer is about 0.71 maybe. But the problem with that is that's not an exact answer. Okay? That's not the exact x-coordinate where the unit circle intersects, the angle intersects the unit circle. So if you can give an exact value as opposed to an estimated value, you would want to do that. And the exact answer is square root of 2 over 2. This is the estimated version of that. And when you're doing a lot of the stuff that you're going to need trigonometry for, you're going to want to give this answer. On quizzes and tests that I'm going to give you, I'm looking for this answer, not this answer. So while yes, you could do this with a calculator, okay, you're never going to get the exact answer. You don't see the same thing that you see here. So what I don't want you to do is just get used to plugging things into your calculator. Now, if your angle's not a special angle, so say you're trying to take the cosine of, say, 72 degrees, just so while we're here, we'll talk about this. The only way to do it is your calculator because it's not going to be able to be done using the methods we have. So the best you can do is an estimate. But if you can find an exact value for anything, okay, if you can find an exact value for anything in the future, you would want to give me that exact value and not an estimated value. Okay, so just think about that as we go through all this. So we have our multiples of 90 degrees, our quadrantal angles. We have our multiples of 45 degrees, and now we're going to look at the last two, which are the multiples of 30 and 60 degrees, which would also be the same as, you know, pi sixth and pi 30. this one being pi sixths, this one being our pi thirds. Alright, we're going to do these together because really 60 is a multiple of 30, so if we can find one, we really are going to get the other one. So we're looking at, say, this angle right here, let's say 30 degrees. Okay? Actually, no, let's do 16 first instead. So let's look at 60 degrees here. Okay? This would be my 60 degree angle, or my pi thirds. Okay? Again, we want to come up with this point. Well, we're going to do a couple of things. This radius here is 1, right? We're going to need a little geometry here. So the radius there is 1. What I'm going to do is I'm going to go and say, all right, well, I'm going to connect these two and I'm going to make a triangle. Well, if the radius is 1, then this side of this triangle is also 1. Well, if the triangle is 1 and 1, this is an isosceles triangle because these two sides are the same, which means these two angles here have to be equal. Again, that's a little bit of geometry. Well, the sum of all the angles in a circle, if you add them all up, should be 180 degrees. Well, if this one's 60, that means these two combined should be 120, but they're equal, which means each of them has to be 60. Now, if all the angles inside my triangle are the same, then what I have is actually an equilateral triangle. So that means this side here is also 1. Alright, so now I'm going to look at this triangle and I'm going to start breaking it down. What I'm going to do is I'm going to take this angle right here and I'm going to bisect it. And I'm going to cut it in half and I'm going to meet the opposite side at 90 degrees. What it does is it cuts this side in half. Okay? If I cut this angle in half, I cut this side in half. Which means if the total length was 1, each one of these pieces is a half. Which right away tells me that the x-coordinate here is a half. Because if I drop straight down 90 degrees, where I hit the x-axis, okay, which is right here, I'm hitting the x-axis at a half, okay, then that should be the x-coordinate for that point. Now once I have the x-coordinate for that point, I can come up with the y-coordinate by saying, alright, well, my point is on the circle, right? If it's on the circle, it's on the equation x squared plus y squared equals 1. So if I plug a half in for x, I can then solve for y. So if I go ahead and do that, let me just jump to something here. So I have x squared plus y squared equals 1. And if I have x squared plus y squared equals 1, we said x was a half, so I get 1 half squared plus y squared equals 1. Okay, so then what does that tell me there? That tells me that 1/4 plus y squared equals 1. Move the 1/4 over by subtracting. So I get y squared equals 1 minus a fourth, which is 3/4. So if y squared equals 3/4, then y itself equals the square root of 3/4. Remember, plus or minus. And that's because there's going to be 2 points associated with this. Then what are we going to have here? This is going to be the square root of 3 over the square root of 4, plus or minus, which is going to be the square root of 3 over 2. So that's my y value, again, plus or minus. So I go back to my picture, the y value is square root of 3 over 2. Now why did I get two different y values? Because for this one x value, there's another angle here that has the same, well, that's a bad picture. Let me erase that, hold on. There's another angle here that has the same exact x value of a half, but the y value, since I'm down here, is negative square root of 3 over 2. And this is going to be the same thing we did with the 45 degrees. The multiple of 60 that's here, the multiple of 60 that's here, right? So this would be 120 degrees, or we could say that this was, what, 2 pi thirds? That point right there is going to be related to this point in that it's going to have the same y coordinate, square root of 3 over 2, but the x is going to be minus 1/2. If I follow it down this way, this is going to have the same x coordinate, minus 1/2, but the negative of the y. What angle would that be? Well, it's a pi thirds angle. They're all pi thirds, right? 60 is pi thirds. This is 2 pi thirds. This would be 4 pi thirds. And then if I go here, this one would be 5 pi thirds, and I have my x and my y coordinates there. So you get these x and the y coordinates from this, you know, rotation around, but it comes from this triangle that we're looking at, and it kind of gets kind of messy when you start to look at all of it. But if you go back to the original unit circle, you start to see that, where these points are coming from that we looked at in the beginning. What I suggest you probably are going to want to do is print a copy of this unit circle out, and I'll have a link to it on the e-learning page. But you should probably print a copy of this out and use it as a reference as you first start it. But eventually what you need to do is put that reference away and just really have these points memorized. So we looked at the quadrantal, we looked at the 45, we looked at the pi thirds angle. Now all we have to do is come up with a 30-degree angle. So let's go back. So if we look at this original picture that we were talking about with the 60 degrees and we made this triangle, I bisected this angle right here, which tells me that if the whole thing was 60, this angle right here is actually 30 degrees. So this angle has 30, this angle 60, and this is a right triangle. What I can do is I can take this triangle and rotate it, okay? And I'm going to put the 30-degree angle here, which will put the 60-degree angle elsewhere. So if I look at it, I'm going to look at this triangle right here, okay? Which is a right triangle. I made the 30-degree angle go here, and now this angle right here would have to be the 60-degree angle. So it's the same triangle that I'm looking at here. I'm just flipping it around and putting the 30-degree, this vertex point here, at the origin. Well, the sides of the triangle should all be the same. So remember, the short side was this distance here, so this should be a half, which that's now the y-coordinate is a half. And if I flip basically what I did is I flipped the x over to the y, so now I'm going to flip the y over to the x, and that's going to be the point for the 30-degree angle. If I follow that around the whole circle, again, I'm going to go back. If I follow that around the circle, I'm just going to go back to this picture. That's the point I'm looking at. Well, the other pi sixth angle is the one straight across from it. That's 5 pi sixths. Okay, that has the same setup, just a negative in the x. I go straight down. Okay, I get the other pi sixth angle, which is this one. That's 7 pi sixths. Okay, and then I get the last pi sixth. I go straight across. This one, they all have the same setup. Square root of 3 over 2 for the x, 1/2 for the y, just positive or negative changing as I move around the circle. So I look at this sort of box of values, just like I did with the 60. These were the 60-degree angles here as I move around. So you're going to have to memorize these points. Now, here's an easy way to do it. I mean, what I've given you is a fairly decent setup of where these points come from, but what you should see is that there's a pattern to all this. And I think everyone should be able to count to 3. And if you can count to 3, you have your pattern. Let's look at the first quadrant. We know that if we get this first quadrant down, everything else around is just a repetition of that. So everything, if you look at it really closely, everything is over 2, right? So if you know that everything's over 2, then just do that. Then all you have to do is come up with these different numerators. Well, if you look at the x values, starting from the top and moving down, 1, 2, 3. So if I know that I have to go 1, 2, 3 on my x's, starting from the top down, I'm going this way, 1, 2, 3 with my x's, I can get the x values along the unit circle. If I go the opposite way, look at the y's, 1, 2, 3. So going this way, I can count the 3, and I get my y values. Everything over 2, 1, 2, 3 going down on the x's, 1, 2, 3 going up on the y's. Once you get your first quadrant down, we know that everything over here is just a repetition of that, everything down here is a repetition of that, everything over here is a repetition of that. So it's a very easy pattern, and I think when you first looked at the unit circle it was fairly intimidating. Now that we've broken it down, it shouldn't be too bad, but it takes a lot of practice. Trigonometry is largely all memorization. So if you can memorize this and practice it, trigonometry is actually not that bad. There are two small things we need to cover to finish this lesson off, and one is reference angles. We've already basically discussed reference angles without really even talking about them. I didn't reference the name, but we've done it. When we said that multiples of pi sixth have the same point associated with it, just changing the positive or negative values of the x's and the y's, that's really the concept of reference angles. So we can look at the reference angle just in terms of its pure definition, but really you're going to use reference angles mainly by looking at, okay, pi sixth, 5 pi sixth, 7 pi sixth. These are going to be angles that as I move my way around the circle, they're all going to have the same point associated with it, okay, in that I'm going to have the x coordinate be square root of 3 over 2 and the y coordinate be 1/2. It's just positive or negative. That's the idea of reference angles, and that's really kind of all you need to know, but we'll look at the actual definition of reference angles real quick. So, definition. If an angle theta is a non-quadrantal angle, meaning it doesn't fall on an axis, is in standard position, then the reference angle for theta is the positive angle, we're going to call it theta prime, we're going to use this notation, okay, formed by the terminal side of theta and the positive or negative x-axis. So what does that really mean? What it means is this. I look at an angle in standard position. So it starts here, and let's say it rotates around to the second quadrant. So that's my angle theta. The angle that I create, that is a positive angle, okay, that is formed by the terminal side and the x-axis would be this angle right here, okay? It's formed by the terminal side and the x-axis. That angle is what we call theta prime. That's the reference angle. If my angle is in quadrant 3, so say that's theta right there, that one right there, we'll just call it beta, okay? That angle right there is beta. The angle created by the terminal side and the x-axis, which would be this angle right here, would be beta prime. If my angle falls into quadrant 4, and it doesn't matter how I got to quadrant 1, 2, 3, 4. If my angle somehow falls in quadrant 4, okay, so whether I went this way or whether I went this way, let's say I went that way, that's alpha. This angle right here, the small angle created by the terminal side and the x-axis, would be my reference angle. So that's the concept of reference angles. Now if you want to find a reference angle, if we just kind of go back, let's erase beta and alpha, and let's just look at theta. If you want to find a reference angle, it's actually really pretty simple. If theta is, I don't know, let's just give you an easy one. Let's say 170 degrees. Let's say that's theta. That would fall in quadrant 2. I need to figure out what this angle is right here. Well, that's pretty easy because if this total thing is 180, right, and this is 170, everyone should know that this is 10 degrees. Well, how did I get that? I took 180 minus my theta, and I got theta prime. That's if I'm in quadrant 2, okay? If I'm in quadrant 3, and I look at it this way, okay, let's say the angle is, I don't know, this is beta now again. So beta would be, I don't know, 200 degrees, okay? I need to figure out what this little one is here. Well, if that's 200, and I know this is 180, everyone should realize that the difference would be 20 degrees. Well, how did I get that? If I'm in quadrant 3, what I did is I had to say, all right, well, I took my beta and I subtracted 180 from it. And that gave me beta prime, my reference angle. Now, you can do this for any angle. If I give you some random angle, you should be able to come up with this. As long as you know what quadrant it is, you know whether or not you do 180 minus the angle or the angle minus 180. That's these two quadrants, okay? If I'm here in this one, let's say the angle is 330 degrees, okay? And I want to find what this angle is right here. Well, we know that if we go all the way around, we're at 360. So the difference is 30 degrees, so this reference is 30 degrees. So how do I get that? Well, I would take my 360 minus my angle, let's say this is alpha, and that gives me alpha prime, so that would be for quadrant 4. And if I'm in quadrant 1, then the angle itself is really the reference angle. This small angle right here is the reference angle. But anyway, so you can do this, but why is this important? Well, you're never really going to do it for random angles so much, but you will do them for their special angles. If I go back and I look at this, All right, here's a couple of examples. We'll do these in a second. If I look at this, we said that if we look at, say, pi sixth, okay, pi sixth, the coordinate that I intersect is square root of 3 over 2, 1 over 2. If I look at 5 pi sixth, okay, which is there, the point here is related to the point there. Why is the point related to that? It's because this little angle right here, which is the reference angle, is also pi sixth. So if this is pi 6 and this is pi 6, this point and this point are related to one another. And that's really the main reason why you need reference angles. Now, while I could give you other examples like this and say find the reference angles, and we're going to do it, the main reason you need reference angles is because of stuff that we've already done, is to show that this point and this point are related. So pi 6 and 5 pi 6 generally have the same x and y coordinates, just one could be negative. Alright, so now let's just do a couple examples of some reference angles and finish that. Alright, so let's look at 125 degrees. 125 degrees, this is probably the best thing to do, is to figure out where it falls. It falls in quadrant 2, right? That's 125 degrees. So if I look at that, if I go back to my reference I was talking about before, in quadrant 2, what you need to do is you need to take 180 degrees minus your angle, and you get theta prime. So for this, I'm going to say 180 minus 125, and that'll get me my answer. So that's going to be 55 degrees. Okay, 2.3 as my angle. Now there's no degree symbol there, so that is radians. You don't always see radians as pi. This is radians, so I need to figure out, okay, where is 2.3 radians? This is not easy. Well, what do we know? We know that if I go halfway around the circle, that's pi radians, which is roughly 3.14, right? And if I go a quarter away the circle, that's pi over 2. Well, that's 3.14 divided by 2, so roughly, 1.5. Now, this is all estimate, right? That's not even close to the, best answer I can give, but 1.5. So 3.14, 1.5, 2.3 is somewhere in between. So there's 2.3. Again, quadrant 2. So if it's in quadrant 2, I do 180 minus my angle, but this is radians. So I'm going to do pi minus 2.3. And that's going to be my theta prime. Now I could leave it like that, that's the exact. Sometimes what you'll see is they'll actually round this and go 3.14 minus 2.3, and then I'll get the answer that way, and that'll be your theta prime. But generally that's how you would do it. Okay? If you left your answer like this, that's right. If you actually did this, I guess that's okay as well. I think you're going to see in the textbook they'll do it that way. And the last one, 2 pi thirds. Well, again, 2 pi thirds falls in quadrant 2, so I'm going to say pi minus 2 pi thirds, and that'll get me theta prime. But that one's easy because you know the reference angle is whatever this is a multiple of, so pi thirds. Okay? And that's the nice thing about radians. You clearly see what this is a multiple of, so you clearly see what the reference angle is. 5 pi 6, it's real easy to see that the reference angle is pi sixth. 7 pi fourths, it's clear to see the reference angle is pi fourths. Whatever this is a multiple of, that's the reference angle. Degrees, you don't see it as well, but in radians you really see it nicely, what the reference angle is. Even if I said, I don't know, one you're not used to, 12 pi fifths, the reference angle for that is pi fifths, because this is a multiple of pi fifths. So if you can just find these reference angles doing this basic computation, you should be alright. The last thing we need to talk about is something called an identity. Now we're going to spend a whole chapter talking about identities. This is just the introduction while we're in this section, and we won't really come back to this for a little while. So an identity is an equation that is satisfied for all values of the variable for which both sides are defined. This equation is going to relate two or more trigonometric functions together. So what it is an equation that's always true. Right? So no matter what angle I can plug into this, This is a particular identity. No matter what angle I plug into this, this equation will always be true. It's satisfied for all values of the variable for which our functions are defined. So if I look at this, I'm going to say, okay, here's an angle theta. No matter what angle I plug in here for theta, if I do sine squared theta plus cosine squared theta, I should always get 1. Now here's a notation thing that you're going to have to get used to, and this idea of sine squared theta. You read that sine squared theta. So what this is it's the sine of theta squared. So if you're going to evaluate this, you would take the sine of theta first, come up with an answer, and then square it. So just this notation is going to be important because we're going to use this a lot. Now this identity relates the sine and the cosine to one another. We know that when we're looking at a point, cosine is the x coordinate and sine is the y coordinate. But you can relate these two together through this equation. And it comes from this equation. X squared plus y squared equals 1. And since cosine is x and sine is y, then I'm really going to have cosine plus sine, cosine squared plus sine squared equals 1. It's just replacing these two equations into that equation. So this right here is what we call the Pythagorean identity, or the fundamental identity. Depends on, what class you're in or what book you're using, what section you're in. They change the names a lot for these things. The name's not so important, it's knowing the identity. It's called the Pythagorean identity because it relates to the Pythagorean theorem, a squared plus b squared equals c squared, which is kind of where this equation comes from in the first place. But it's also called the fundamental identity because it's the one that you're going to use most often. You're going to use this identity over and over again. All right. So how would we use it right now? Well, it's an equation that relates these two functions together. So if it relates these two functions together, it means if I have the answer for one of them, I can get the answer for the other. So if I'm trying to find the value for the cosine of theta, but I know that the value for sine of theta is 3/5, even though I don't know what angle specifically theta is, if I know one of these, I can come up with the other one. This is another key part to this, is because the angle is in quadrant 2. Knowing what quadrant your angle's in will tell you whether your answer is going to be positive or negative. So what I'm going to do is I'm going to say, okay, sine squared plus cosine squared theta equals 1. Sine is 3/5, so that means 3/5 squared plus cosine squared theta equals 1. So it tells me that cosine squared theta equals 1 minus 9 over 25. If I square this, I get 9 over 25, subtract it to the other side. This tells me that the cosine squared of theta equals 1 minus 9 over 25 is 16 over 25. Because 1 is 25 over 25. I'm going to say that cosine of theta equals the plus or minus the square root of 16 over 25. Because you're going to get rid of the square by taking the square root. Which is the cosine of theta equals plus or minus 4 over 5. Now I got two answers, plus or minus, and that's where this comes in. If my angle is in quadrant 2, cosine is always the x-coordinate in the unit circle. X-coordinates in quadrant 2 are negative, so the answer I want here is that the cosine of theta equals negative 4/5. And that would be my answer. But what you're getting out of this is that once you know one of these, you get the other one. And I could go either way. And it's all through this identity. Because this is an identity that relates the sine and the cosine to one another, and it's always true for all values of the variable.